Thank you very much for the invitation to speak here in Vienna. And also I want to thank the participants for being here in this situation. So I think that it's nice to see people again in a conference. So it's really encouraging. So I want to say, first of all, that this is a joint work with Alejandro Cabrera, that is professor at UFRJ in Brazil, at Rio de Janeiro. And this is a work in progress, so it's not already even in the archive, but I hope that all the results are correct that I want to present today. The second thing that I want to say is that this was already presented, or an earlier version of this result was already presented in December in Rio de Janeiro in a conference there. And there we've given the particular case when the Manin triple was given by the graph of a Poisson bivector. So right now we are extending, and we think that this, okay, a quite nice result right now. And the other thing that I want to say is that this talk basically leads on two things. In one hand, we have this AQSC sigma model and our field theories and these kind of things. And in the other hand, is purely Lie theoretic talk. So like integration of Lie algebroids to Lie groupoids and these kind of things. So I will try to be like assuming less things as possible in both sides in order that most of you can follow the talk correctly. So, but I know that the background that some of you have can be really different as mine, so I hope that you will understand the talk. Okay, so let me just start to fix our framework, and the framework is this AQSC topological sigma models that we already seen it in Ikeda's talk or in Severa mini course. So what we need to define these kind of sigma models are just a d-dimensional manifold and a d-1 symplectic Q manifold. That means a graded manifold of degree d-1 with a symplectic form that I am required to be exact. And the homological degree is d-1, and then I have this chart, this function here of degree d satisfying this classical master equation. So these sigma models have, as the space of fields, just the maps between two graded manifolds. In the source, we have the tangent shifted by 1, so differential forms on my d-dimensional manifold. And in the source, I just have this graded symplectic manifold that can be whatever thing. Okay, so now given this topological information, I can produce an action that is just a function on the space of fields that is of degree 0, of homological degree 0, and this function is given by this strange formula here, that is just the pullback of this one form contracted with the Dirac vector field on the source, plus the pullback of this char here, this theta. And what happens is that, well, since I'm choosing these dimensions and degrees, they are these transgression formulas, and therefore this have homological degree 0. That is what I want. And now, this Batalin-Vilkovsky formalists realize just in the fact that on the space of fields, in our graded manifold, we have a symplectic form that is just the pullback of the form on the target that have internal of homological degree -1. And then this action satisfies this master equation. So the bracket with itself, the Poisson bracket with itself is equal to 0. And I think that this is more or less standard, and you are more or less familiar with this kind of things. And what we introduce in this talk is the boundary conditions that we want to use. So there are many different ways to introduce boundary conditions, but the one that we will use it are just given by Lagrangian submanifolds, Lagrangian Q submanifolds of the target. Okay? So this kind of boundary conditions sometimes are called branes. And as opposite to this BFB formalism, where you just allow free boundary conditions, this is something that you choose and you need to fix. And then when you fix that, what happens is that the space of fields, you are taking a subset of the space of fields that I already defined it at the beginning. So I'm just restricting my space of fields to the ones that satisfies these boundary conditions. That is what I have. And this is the main character of today. And my dream is to try to compute the path integral. So to fully compute your topological sigma model, and this is what we dream to do, and we are, I need to say, not able to do it right now, then we will try to find another thing to do. And as you see, in order to compute this path integral, this appears here on some manifold, and this submanifold is just a Lagrangian submanifold of the space of fields, and this is called the gates fixing. And this, more or less, what if I choose a right Lagrangian submanifold, this is what, I don't know, for different techniques, maybe I can compute this path integral with a bit of luck. Okay, so this was really abstract, so just let's go to an example. So when d is equal to 2, I just have a surface, and then degree 1 symplectic Q manifolds are the same as Poisson manifolds. So how is the equivalence going? Given a Poisson manifold, I can consider just the cotangent shifted by 1. And since it's a cotangent bundle, I can put just the canonical symplectic form of the cotangent bundle. And this have degree 1, because I'm shifting by 1, as I want, and happen that is exact. Okay, and now, you see the functions on these manifolds, on these graded manifolds, on these shifted cotangent bundles are just multi-vector fields. So a degree 2 function is just a bivector field on M, and satisfy this classical master equation is just that pi is Poisson. Then, what happens is that the classical space of fields, so the degree 0 of these graded manifold maps are given by two fields, this y and theta, and the classical action is the well-known Poisson sigma model action that we already know. Okay, and the boundary conditions that we can impose in this case are just given by coisotropic submanifold. So one can compute that given a coisotropic submanifold, I just pick the conormal bundle, and this gives me a Lagrangian submanifold of the given type that I want. And I just want to remark that in this case, the path integral was computed, and if you choose sigma to be the disk, and you choose a particular observable, then you obtain the Kontsevich star product. That is a really nice result, and something that you want to have, like in general, some kind of computation like that. Okay, so let's go to another example, d equal to 3. And for d equal to 3, what happens is that the degree 2 symplectic Q manifolds are the same as Courant algebroids.
I just would like to make a short remark that the Courant sigma model was, I think, first found by Ikeda. One should just
thank you.
Yeah, just to my knowledge.
Yeah, thank you for advising me that. So how this correspondence should go is in the following way. Given a Courant algebroid, I can declare a graded manifolds where the functions in degree 1 are sections of my vector bundle, and the functions in degree 2 are just derivations of my vector bundle that preserve the pairing. And it happens that this glue well and deforms a degree 2 manifold. And then the pairing in this degree, the pairing produces you a symplectic form in this degree 2 manifold. And the formula where I have chalk here. The formula EA, EB, EC produce you a degree 3 function on this graded manifold. And this is how more or less the correspondence go between Courant algebroids and degree 2 symplectic Q manifolds. And now one can even go further and see that the Lagrangian Qs and manifolds correspond to Dirac structures, maybe with support or whatever, but they are Dirac structures. So one can define now just a sigma model by giving a 3-dimensional manifold and a Courant algebroid, and then the EQSEED recipe tells you that you have right now 3 fields, and you have this action that looks quite intimidating. And then you can say, okay, I can fix boundary conditions for this sigma model given Dirac structures. And now the question that we will try to solve is this one. Can we expect any relation between the Courant sigma model and the Poisson sigma model? Is there any kind of dimensional reduction from one to the other? And well, the answer is yes, and is related to Lie theory. Okay, so in order to answer this, and the first thing that you should ask is, okay, I have in one side Courant algebroid and Dirac structures, how we can produce Poisson geometry from that data. Where is the Poisson geometry here? So the Poisson geometry is just secretly over there, and you need to look a bit to find it. So suppose that you have just a Courant algebroid and you have a Dirac structure. Then choose just any vector bundle that complements to this Dirac structure. Then, by the pairing, you can identify this complement with the dual. And then what happens is that this dual inherits some kind of structure, some kind of bracket and anchor just by restricting the structure of the Courant algebroid, but these don't satisfy nice properties. But on a priori, what we can say is that we have a bivector field and a 3-vector field just induced by the structure that this complement arise. And what happens is that these things glue together and they are called Lie quasi-bialgebroids. So now suppose that you are really lucky and what you choose, this complement, really is a Dirac structure. So what happens is that Dirac are Lie algebroids, and then the dual of a Lie algebroid inherits a linear Poisson structure. And then you can transpose this linear Poisson structure into A, and this is the data that you have. So a Poisson structure appears once you choose a complement that is good enough. So that is also Dirac. And this is our definition of Manin triples, so it's not our. Pi A is an ordinary Poisson structure on A. Yeah, a linear one. A linear Poisson structure.
A viewed as a manifold or what?
A viewed as a vector bundle. So
no, but what does it mean, a linear Poisson structure on a vector bundle? You mean the vector bundle A viewed as a manifold and you have a Poisson bracket on it?
Yeah, and you have a Poisson bracket that the coordinates are linear. That's right. So in the moment that I assume that the complement is Dirac is when I have this Lie bialgebroid thing. So yeah, so a Manin triple is just a Courant algebroid endowed with 2 Dirac structures that are complement, so that are transversal, so that the sum all the Courant algebroid. Okay? And therefore, one can identify one with the dual. So let me just say that these have a supergeometric interpretation in terms of Lagrangian tubular neighborhoods. So suppose that I have my Courant algebroid that is isomorphic to my degree 2 symplectic Q manifold. Then I choose my Dirac structure and I shift it by 1. I give A1, and since it's Lagrangian, then I can just make this Weinstein tubular neighborhood theorem, and then I identified my manifold. Normally it's locally, but right now, since all is linear, is globally. I can identify my manifold with the shifted cotangent bundle. And then the Q structure in this shifted cotangent bundle becomes of 3 pairs. So if you are lucky, so if the tubular neighborhood that you choose is just basically given by a Dirac, then the Q structure have just 2 pieces instead of 3. And yeah, and this is some condition that you need to impose, and is what we are imposing. That you have a complement that is also Dirac. Okay, so once we have that, let me just go a bit further on Lie by algebroids. So a Lie by algebroid is just a Lie algebroid such that the dual is also a Lie algebroid and both structures are compatible. Or analogously, I can say that I have just a Lie algebroid endowed with a linear Poisson structure satisfying that infinitesimally is multiplicative, so a cocycle condition, basically. And what happens in this kind of theory is that the roles of A and A star are completely dual. So A is a Lie by algebroid if and only if A star is a Lie by algebroid. And well, so let me just say that for those that don't know, Lie algebroids are the analogous, basically, of Lie algebras, but you replace just vector space with a vector bundle, and you know that Lie algebras are integrable by Lie groupoids. So here is not quite true, but it's almost true. So in general, you can say that given a Lie algebroid, you can produce some sort of Lie groupoid, and if it exists, you can just choose one that is or simply connected, whatever that means. So the theorem given by Mackenzie Xu more than 20 years ago is that in the case of Lie by algebroids, so suppose that your Lie algebroid is integrable, then what happens is that the groupoid that integrates the Lie algebroid inherits also a Poisson structure that is compatible with the groupoid structure. And this is what is called a Poisson groupoid. And these Poisson groupoids were used or invented by Alan Weinstein in order to unify Poisson Lie groups and symplectic groupoids. So you can think that somehow the theory of Poisson Lie groups and symplectic groupoids can just thought together using these Poisson groupoids. And this is what somehow will appear in our work because we are considered these Manin triples that are the same basically as Lie by algebroids. Okay, so right now we have all the ingredients and we can just state our result. So the result is the following. So suppose that you have a Manin triple, so a Courant algebroid, endowed with 2 Dirac structures such that the 2 Dirac structures are complementary. Then the Courant sigma model given by source just a surface, a closed surface and the interval target the given Courant algebroid and boundary conditions defined by one of the Dirac structures, let's say A prime. So this Courant sigma model admits a gauge fixing such that gives you a dimensional reduction into a Poisson sigma model. So for the Poisson sigma model, we need a 2D manifold that is just sigma, and we need a Poisson manifold. So the Poisson manifold that it appears is just the space of R rows of the Poisson groupoid integrating your Lie algebroid A, that is the one that is complementary to the one that you put in the boundary. So let me draw a picture. So
what do you mean by dimensional reduction?
yeah, that's a good question. I will try to answer during the proof of this statement. So this is sigma and this is I. So I just put in on the boundary, on the two boundaries, I'm putting A prime that are giving this Dirac structure, and somehow orthogonal to this A prime, I have, or transversal to this A prime, I have my direction A that will be auxiliary and is what allows us to just going from one to the other. So what Thomas asked is really a good question. What means dimensional reduction? And basically, so, okay, maybe I can skip that in order, oh, maybe it's too long. Okay. So what I want to say by dimensional reduction is the following. So recall that I have my path integral that is somehow, yeah, maybe you, okay. So recall that I have my path integral that looks like somehow like this. So I want to say that this path integral, once I integrate out, integrating out some, let's say, high energy fields, some ultraviolet sector give to the same path integral in the Poisson sigma model. And this is what we will compute.
But you also call it gauge fixing. So now what confuses me is usually the result should not depend on gauge fixing. However, your target space gets completely different depending on your choice of gauge. That's very strange.
That's right. So the gauge fixing is this. And what happens is that some part of the gauge fixing is depend on this transversal direction. So in fact, so let me say the following. So in Pavel's talk, so what happens in Pavel's talk? So in Pavel's talk, we seen it that he have a Courant algebroid that is G, and inside he pick a Lagrangian submanifold, okay? And then he somehow describe some sigma model that have some kind of dimensional reduction with target G over H, okay? Now suppose that this H is complemented by some H prime. So what happens is that near the unities, so this thing is equivalent to this. Okay? So therefore, what happens is that our gauge fixing is dependent of this transversal direction, but what the Batalin-Belkoditsky procedure tells you is that, okay, you can use it as a gauge fixing, but doesn't matter because all the gauge fixing are equivalent.
Yeah, but the result is not equivalent, so it cannot be equivalent, no? If you get completely different targets, no, or maybe, I don't know.
Well, you can get it, but will depends on this transversal direction. The Poisson structure is more or less the same. No, the Poisson structure is more or less the same. What differs is the groupoid, so the topology of the manifold. Yeah, that's it. Yeah, that's it. So near the units, all the things are the same, but the global topology will depend on what it appears. So maybe, yeah.
So it doesn't seem to be independent of this choice of gauge, right? The result.
Well,
different results.
Sure, sure. Depending on...
So maybe it's not a choice of gauge.
Well, it's a gauge. So maybe I can go through the details and we will see it where it appears and where not. Okay, let me say the following. So, yeah, I can. Okay. So let me say the following. So this result, it already appears in the literature. So, but in the case when the Poisson structure is equal to 0. So when the Levi algebroid is trivial. And then what happens is that the groupoid that integrates the Lie algebroid is just the vector bundle with the addition. And this was more or less an inspiration for us in order to try to do this nonlinear case that is rather non-trivial. The second thing that I want to say is that these kind of boundary conditions are really similar to what Pavels is using, but we are just using topological ones. And one of the things that maybe I want to say right now is that if you have a Lie algebra with your Lagrangian subalgebra, you can make this quotient because a Lie algebra is integrated by a group, a Lie subalgebra is integrated by another group, and you can do that. But if you have a general Courant algebroid, okay, where you integrate your Courant algebroid? The Dirac structure, you can integrate it to a groupoid, but how to make this quotient? So we have a replacement of that quotient by just choosing this transversal and identify it with this transversal thing. And the other thing is that for Chern-Simons, some kind of integration from Lie algebras to Lie groupoid cocycles is appearing also in this holography paper of Pavellon, Miquel Cueca, and Konstantin Wertenlin. Okay, so let me try to convince you that this dimensional reduction result is interesting just by looking into Manin triples that maybe you know. So if you have a Lie algebra with an R matrix, that defines you a Manin triple. If you have a Poisson structure, that defines you a Manin triple. If you have a perisymplectic structure, that defines you a Manin triple. If you have both structures, that defines you a Manin triple. If you have a Poisson-Nijenhuis manifold, that defines you a Manin triple. If you have a twisted Poisson manifold, you also have a Manin triple. Or if you have a complex semi-simple Lie group, you also have a Manin triple given by something called this Cartan, Dirac, and Gauss Dirac structures over there. So there are plenty of situations of geometrical objects that are codified in Manin triples. Each of these kind of things give you results that on the boundary you put one of the structures and then you integrate the other one to the groupoid, and you have some relation between the Courant sigma model and Poisson sigma model of these kind of things. So we believe that many of them are not studied, and this can be another approach to study these kind of things. So let me say also some consequence, and this was like the picture that I tried to define over there, and that you need to have in mind. So in the boundary, you put one of the Dirac structures, and the other one somehow is parameterizing the interval direction. Okay? So let me say that our thing is happening on a cylinder, but if you have an arbitrary three-manifold, just in a neighborhood of one boundary component, you can find this cylinder, and therefore you can see our result just as a Polar neighborhood result for Courant sigma models with one boundary component. Okay. The second thing is that what we were discussing. So is this really gauge dependent, gauge independent? So what happens is that the Poisson structure is independent of the choice of A that we make. But the topology of the groupoid, where you ended, is completely depends on A. So you can have different gauge fixing that give you different Poisson sigma models in the target. But that's not a problem, because what you want to compute at the end is the big integral, and then you can compute it using different gauge fixings. That's what I want to try to say. And the third thing that I want to say is that our result can be seen as a linearization result. So suppose that you start with a Poisson sigma model on a highly non-trivial manifold that is just a Poisson Lie group. Suppose that I want to study the Poisson sigma model of a Poisson Lie group. So I can pay the price of increase the dimension of the source by 1 and to put boundaries in the game in order to study something that is much more simple, that is just Chern-Simons on the algebra that is the dream field double of my Poisson Lie group. Okay, and then for Chern-Simons we know a lot of things, but for the Poisson sigma model of this Poisson Lie group, maybe it's rather complicated to study. And the last thing that I want to comment is that, you know, A and A dual, there is a Manin triple, so you can switch their roles. So if you switch their roles, even if one is appearing in the boundary and the other one is appearing in the gauge fixing, what happens is that maybe you can try to find some kind of duality between different Poisson sigma models on dual Poisson Lie groups. So we don't know yet how this can be done, but we expect this duality thing to try to clarify on our forthcoming works. Okay, so let me give just an idea of the proof. And for that, the proof have just two main ingredients. So one is the mapping space between supermanifolds and their adjoint property. So the point is the following. So given graded manifolds, the category of graded manifolds is just based by graded manifolds, and the morphisms are degree preserving things. So in that category, I can define just the Cartesian product of graded manifolds. And what happens is that the morphisms don't satisfy a nice adjunction property. So what happens is that I can define a new graded manifold given a pair of them, that is the maps between them. And this new graded manifold is defined by just this adjunction property here, or exponential property of the mapping space. And this exponential property is what allows me to put the M inside or outside, and we will play with these kind of things, just decomposing the interval, T1 of the interval, and try to see why this reduces. And what I want to say that will be really important for us is that normally this mapping space is rather complicated, manifold, infinite dimensional, whatever, but there is a remarkable case where everything is finite dimensional, and is when the source map is just R1, and then the result is just the tangent shifted by -1. Okay. And the second main ingredient is how you can construct the groupoid integrating a Lie algebroid just by looking into path modulo homotopies. So let me recall that construction. So suppose that I have a Lie algebroid, then I can look into path on the Lie algebroid, on the vector bundle, and I say that this path is a Lie algebroid path if it's compatible with the anchor in that way. So just what I require is that the projection of that path to the manifold is just the same as going with the anchor. Okay? And now I can define two paths to be equivalent if I have an homotopy between them. And this homotopy is just a map from the square such that is also a Lie algebroid map. And you can express in this kind of conditions. And the theorem is that the space of a path modulo a homotopies is precisely the groupoid integrating your Lie algebroid, in the case that is a manifold or whatever. Okay, so these are the two main characters of the proof of our result. So let me say which is more or less the strategy of the proof. So in the first thing, what we do is just integrating out over some symplectic vibration on the space of fields. So this can be seen as a kind of Losef trick where you identify that. So locally, you can say that I identify in my space of fields as a product manifold of two symplectic manifolds. And then on each symplectic manifold, I have my gauge fixing, my Lagrangian submanifold is also a product. And then I have that the integration, this path integral, is just equivalent to the other one, just by localization and integration out one of the manifolds. Okay, and this is what will happen in our case. This is the basic field theoretic claim that we will use. So here it will appear some delta factor that will depend on the integration over this F2. And this is how we use this A as a gauge fixing in some of the sector that will appear over there. And the second main character is just that this effective theory that we produce on this sector F1 that is localized over some delta factor have a remaining symmetry that you can identify. And this remaining symmetry is just one can quotient out, and then we obtain just the Poisson groupoid that integrate the Lie algebroid A, and this just means basically quotient but A homotopies.
So is it true that you call gauge fixing the splitting of fields into low energy and high energy modes? Like this L1 times L2?
No, what I'm calling gauge fixing, so this splitting will appear by the fact of we identify our Courant algebroid with the cotangent bundle of one of the boundary conditions. But what happens is that this L2 will be also given by the transversal Dirac structure.
Yes, so maybe it's not a gauge fixing, maybe it's more a partial, you integrate out only part of the fields. Yeah. And then it's not so surprising that the result depends on this choice. Because gauge fixing, the result should be always the same, in principle at least. But you do more than gauge fixing, you apply this, so what you call Losef trick. And so you integrate out some modes and leaves out, and then it's not surprising, it depends on the choice of what you integrate out.
Yeah, so what we are calling is, what I call it gauge fixing is this integration out, this high energy, okay, thank you. So what happens is that, we are integrating out this F2 factor, And then this integration out depends on this transversal direction that we choose. Yeah. And then there is, some localization and then some symmetry that you can even go further and quotient out. So this is what is happening. So let me just give some details of these two steps. So as I was trying to say, when you have a when you have a Manin triple, you can identify this degree to manifold with the cotangent of one of the things. And then what happens is that, the space of fields is what you defined here with this boundary condition taken on the dual, that is what I call it A prime at the beginning, and then the action is just given by the acid action. Okay, so the important thing right now is the following expansion property. So let's use the exponential of the maps. So I have T1 of sigma times the interval, that is the same of T1 of sigma cross T1 of the interval. And now T1 of the interval decomposed as the interval times R1. And now this R1, I can just put it inside using the exponential property, and I obtain this T minus 1 of my manifold then. Since I'm identifying M with this cotangent bundle, then I can say that this tangent shifted by minus 1 fits on this double vector bundle picture. And the proposition is that this Q here is a symplectic fibration. Even more, in each fiber, I have a Lagrangian submanifold induced by the other vector bundle structure. So basically, what happens is that one of the sectors will be given by this T star 1 of A, and the other sector will be given by the fiber. And this is the symplectic fibration that we are integrating out. Okay, so right now, just how the localization happens is that inside of the cotangent bundle shifted by 1 of A, I can think that this is a vector bundle, and even more is a BB algebroid. So it's just the cotangent algebroid of the Lie algebroid A. Okay, so as I already said, inside of maps from the interval to a Lie algebroid, I have the algebroid path, the A path, and this is C. And once more, using just the exponential property of the maps, I can define this curly C, just the maps taking values on A path. So the field theoretic claim that we have is that the Courant sigma model action just is equivalent to some kind of this SA, some kind of action that just depends on the canonical symplectic form of the cotangent bundle and the Poisson form on A, localize it over the cotangent algebroid path. So this is the delta factor localization, and this is the action, the effective action somehow, and this is the Courant action that we have over there. Okay, so for those who love coordinates,
this delta C, is it also something which follows from the field equation of this Poisson signal model or not? I'm not sure what this FA precisely was.
So I think that you can see it here. So this delta C are these two equations here.
Yeah, but can you go back to the previous? So you have SA is the Poisson signal model or not?
No, S is excuse me, not yet. It's like somehow the Poisson sigma model, but you see, it's not yet because I have the interval here. It's like the Poisson sigma model, but on a 3-dimensional manifold.
But its equations of motion would also implement C equals 0. I mean, this localization.
I think so.
Yeah. Mm-hmm.
Yeah. So for those who likes coordinates, I can say that, okay, the number that appears behind the coordinate is just the degree as the graded manifold as the coordinate, the homological degree, and the color says which coordinates are dual to each other on the symplectic form. Okay, so if I have my Courant S action, that is this long thing here, so I have some topological term at the beginning, and then the terms depending on the bialgebroid structure. Then I can give two sectors, give it by 4 coordinates each sector, and then on the ultraviolet sector, this F2, then I just pick the gauge fixing given by the Lie algebroid conditions on A. And then what happens is that this action just have the formula of SA plus this term here, and then since P and A are interlineary, I can implement this delta factor, basically. So this is the first part, that is how the localization over A path appears. And the second part is how to produce the groupoid thing. So as I was saying, what happens is that we just put it inside one of the part of T1 of the interval. So now we need to put the whole interval inside. So for that, recall that I constructed the groupoid as just the path modulo homotopes. And what happens is that if I have a form on the Lie algebroid that satisfies some cocycle conditions, so infinitesimally multiplicative, then I can cook up some form on the groupoid that satisfies this diagram commuting thing. So can be integrated to the groupoid, basically. So, and this is what we will use. So right now what we have is that what we are considering is the cotangent of a Lie algebroid that is also a Lie algebroid, and the groupoid integrating the cotangent is the cotangent of the groupoid by just everything shifted by 1. And now on that Lie algebroid, I have two forms. So one is a 1 form, that is the canonical 1 form on the cotangent, and the other one is a 0 form, so just a function. And recall that functions on the cotangent bundle are just multi-vector fields. So this is why the Poisson tensor can be seen as a form. And then, once more, I use the exponential of the maps in order to put this sigma inside. And the result is that you have a relation between this SA that I construction and just the Poisson sigma model action on the groupoid, on the usual groupoid. Okay? And this is just a Lie theoretic claim. So there is nothing about like field theories or infinite dimensional things. So it's all under control. And just let me just put everything together. So in the first step, we appear over this delta factor. In the second step, we integrate the homotopies, the remaining gauge symmetries, and then what you can see in it is that what appears at the end by this partial integration then give you just exactly the space of fields are the Poisson sigma model on the groupoid, and the action is the Poisson sigma model on the groupoid. And the way you pass from one to the other is just by this partial integration over one of the sectors that is just gauge fixing, one of the sectors by this transversal condition that I have on A. And this is more or less the proof. And just to end it, I just want to say that there is another way that is also interesting to consider and give you somehow also a nice formula. That is, instead of quotient these homotopies, I can also gauge fix it. And the way that I can do that is just by using a Lie algebroid spray that is just a linear vector field, once more compatible with the anchor. And this, what give me is just an identification around the units of my groupoid with some chosen A path given by these spray conditions. Okay? So in particular, if we consider the Lie algebroid, the Courant algebroid just the standard one, and the Manin triple given by a Poisson by vector, and we choose an spray, then what our proof recovers is this Kreinin-Markut formula for the symplectic form on the groupoid that integrates the Poisson, your Poisson manifold. That is, I think, is nice and concrete. And just to end, just some future projects that we have. One is really try to compute some perturbative computation. Maybe I hope that I can learn it, this propagator that Pavel is proposing, and this can help us to make some kind of computation there, quantum computation over there. The other thing that maybe you can try to do is just include other kind or boundary conditions also in sigma. So corners, basically, given by quasotropics and manifolds on your Poisson sigma model. And I think that this should work more or less smooth. This should be easy. And the last thing that I want to say is that, well, at the beginning, what I was trying to do is to use the Courant sigma model to compute Morita equivalence between the star products, quantizing some Poisson manifolds, and this is why I was interested into some relation between the Poisson and the Courant sigma model. And we are not able yet to see if that's the case, but I think that maybe it's a good idea to try to include Morita equivalence between Poisson manifolds in this Courant sigma model picture. And well, that's all. Thank you very much.
Thank you very much.
Okay, other questions?
So, as you said, the Poisson sigma model is probably most useful when it's considered on a disk with this kind of standard boundary condition. So, if you do it in your case, do you get with just a ball with simply your boundary condition everywhere on the sphere?
Maybe.
But it's just kind of, let's say, reasonable suggestion that you would take like a cylinder and then you squeeze those sides. And then, okay, if it's true, okay, I guess that Lie algebroids or Lie quasi-algebroids are not quantized yet, but still, supposing that, so your project might lead into that in the end. But then it would look like that you have this ball, and then on the equator, you might be putting some insertions.
Okay.
But in principle, then those insertions might be anywhere. They don't have to stay on the equator. You can put them wherever you want, even though you might lose this interpretation in terms of the Poisson sigma model. But then it would mean that actually there is kind of maybe more structure, like more like a E2 structure than just E1 structure for those Hopf algebroids. So, I don't know, maybe it's a stupid question, but is there any statement like that Hopf algebroids, not just Hopf algebras, lead to what may be equivalent to some kind of braided things?
So it will be very nice, but I have no idea of how to answer that. So in fact, what it suggests this is that if you start with the dream field double, you end it with the Poisson Lie groups. And then, okay, the Poisson sigma model, I don't know how it's related to the Hopf algebras of these Poisson Lie groups, but I hope that maybe there is a way to do this kind of things, and I will be really happy to discuss that point.
Thanks a lot. Any other further questions?
The examples of Manin triples that you showed us at some point were basically exclusively vectors plus one forms. Is there some example or some possibility to have something else, like vectors plus two forms, for example? Do you know of such an example that you could include in your...
So you want to see, so here you have like a two form. So
No, I mean the vector bundle is t plus t star in all cases.
I see your point.
So could you have t plus wedge square t star, for example, and still do something?
Yeah. This is something that you can do it, but you didn't end up with a d-dimension. So this is, the Courant sigma model is three-dimensional. So if you want to put Tm plus wedge 2 of T star m, you go further dimensions. And then, in fact, something that we have is some kind of dimensional reduction in the case where you have, in this case, the presymplectic manifold case. So we have a K, the graph of a K form inside of this manifold, and then we can produce some dimensional reduction from this kind of Tm wedge K minus 1 of T star m into the Courant, into some higher Courant algebroid that is Tm plus wedge K minus 2 of T star m by shifted or twisted by this K form. So I can explain to you. So we have some kind of result going also in that direction.
Are there further questions? Are there online questions?
Can I ask a question?
Sure, go ahead.
I'm Ikeda. Okay?
Yes.
Yeah, I'm glad if you cite my name in the Courant sigma model. I did one comment.
Yeah, please ask a question. We hear you.
Yeah. I think there is a possibility to get more general sigma model than Poisson sigma model in the dimensional reduction. Is it right?
So if I understand well the question, so
do you?
yeah.
Maybe there is a more general. We can obtain more general model.
Yeah. So
sigma model in the dimensional reduction. Is it right? Is it right? This is the question. My question.
yeah. So all our work leads on the condition that we are considered a Manin triple. So if you pick this transversal to be just any complement, you obtain these Lie quasi-bialgebroids, and then can be right that maybe there is some kind of twisted version there when you can produce some interesting things just by picking some transversal property, some arbitrary transversal without demanding that being also Dirac. And this will be more general than a standard Poisson sigma model.
What occurred in that case? Or what, for example, maybe we can obtain the Dirac sigma model. Is it right?
Maybe. I have no idea. I will be glad to discuss that question because as you see, it's not really a super strong condition to demand that your boundary condition have a good transversal to be also Dirac, but it's some kind of condition. So if you can weaker, then will be good. Yeah.
Thank you.
Okay, any more questions? There's one more question.
Yes, you mentioned earlier to me today that you were particularly looking at the case of any Poisson structure as a Dirac structure in the standard Courant algebroid, with the dual gauge fixing structure being just the zero structure, the detection bundle. So what happens in that case?
So in that case, the groupoid is just the fundamental groupoid, sorry. And therefore, what you obtain is that you go to the boundary, so you start with the Courant algebroid with boundary the Poisson structure, and then you reduce to the fundamental groupoid of your manifold M with Poisson structure, just the multiplicative structure in the fundamental groupoid. And one can go even a bit further with results of Alejandro Cabrera that relates this structure there to the Poisson sigma model on just on M. But this requires some additional techniques. So in that case, it's interesting to notice that where you ended is not on your manifold, but on the fundamental groupoid of your manifold.
Do you really need this so simply connected integration? Couldn't you do everything with a formal integration?
A priori, you need, because the symmetries that you need to quotient out here are the gauge homotopy. So the way that the groupoid that you ended is just on A path modulo A homotopies, and this gives you naturally the source simply connected one.
You need large symmetries.
Yeah, but maybe using this sprite procedure, you can just end it on a neighborhood of the units, and yeah. So there are different procedures that you can end it on different kind of things.
Thank you.
Thank you.